Hi friends, in the previous videos I explained various assembly language programmings of 8086 which include arithmetic related programs, logical related programs, sorting arrangement related programs, okay, and string related assembly language programmings of 8086, okay, and in that I also give an overview of MASM directives, how to write the assembly language programming. Now coming to this particular video, I explained briefly about the pin description of 8086. Nothing but how many pins are present, what is the function of each pin. We'll see in detail here. Okay. Okay, let us see. I am making a presentation into full screen mode. Right. So let us see. This is the pin diagram of 8086. Here, let us see how many pins are present. Generally, 20 in one side, 20 in other side. Total number of pins present in 8086 processor is 40 pins. So see here there is one. Then bottom to top. This is the arrangement. Okay. So 1 to 20, then from 21 to 40. Like that we are arranging. So advantage of this 8086 is some pins are multiplexed pins. Because of multiplexed nature, what happens? We are saving the number of pins. Then the size of the 8086 chip is very small. Okay, for that a few multiplexed pins are there. Let us see in detail what are the multiplexed pins and all. Right. So first pin is ground. Then AD14. AD14 is it's a multiplexed address and data. It's a combination of address and data. It's the 14th bit. Similarly, AD13 multiplexed address and data 13th pin. Like that, AD14 to AD0 related to multiplexed address and data lines. See other side, 39th pin is AD15. Okay. Then next A16/S3. Similarly, A17/S4 like that. A19/S6. Similarly, BA/S7. Then 8086 operates in two modes, minimum mode and maximum mode. So if it is minimum mode, see here pins that especially 24 to 31. 24 to 31. If it is minimum, we have INDA bar, ALE, DN bar, DT by R bar, M by O bar, right bar, HLD and hold comes into picture. If it is maximum mode, we have these 8. Nothing but to QS1, QS0 like that, S0, S1, S2, then log bar, request bar by grant 1 bar like that. These 8 will come if it is maximum mode. If it is minimum mode, these 8 pins will come. Okay. Okay. Like that, 8086 provide some space. Okay. Provide less space in order to make all these pins. Right. So depending on the selection of pin number 33, we have either this 8 or this 8 will comes into picture. Like that, they saved 8 pins. Instead of, for example, if you take minimum 8 pins, maximum also separately 8, then number of pins are increasing. Instead of 40, it will go to something like 48 or something. Similarly, here we don't have separate address and data lines. We have 16 address lines multiplexed with 16 data lines. For example, if they are separately available, we have separate 16 address lines and separate 60 data lines. So we have 16 more pins. Similarly, some address lines are multiplexed with S. S means status. So these pins are also multiplexed. Like that, wherever possible, function of each pin. Let us detail what is the function of each pin. First, coming to ground. Okay, we know what is the role of ground. Ground pin is mainly used to make protection against any short circuits. Generally, this pin is connected to ground. Okay, so if any problem is occurred or any short circuit problem is occurred, then this ground pin will provide protection. Okay. Now coming to address lines here, AD0 to AD15. Okay, AD0 to AD14 this side AD15 here. So AD0 to AD0 to this is AD0 actually. AD0 to AD14. Let us see function of AD0 to AD14 and AD15. So we know already all these. So they are not pure address lines and they are not pure data lines. So these lines are multiplexed address and data lines, nothing but combination of address and data. For example, processor wants to read data from external memory, or processor wants to send data to external memory. In that case, what happens? We should separate these multiplexed address and data lines into pure address lines and pure data lines. So in which way we are separating these lines? Generally, this AD0 to AD15 multiplex address and data lines are separated into pure address lines and data lines by using external latches and ALE signal. So there is one signal called as ALE. Let us see here ALE, pin number 25. Okay, this is important. ALE, full name is address latch enable ALE. So with the help of this ALE signal, 8086 can separate multiplex address and data lines into pure address lines by using external latch. Generally, one latch can separate only one latch. If you take, it will separate only 8 multiplex lines into pure address lines. But here AD0 to AD14 plus AD15, total 16 multiplex address and data lines are there. So we need 2 latches along with ALE signal. Then we get pure address lines. So like that, this ALE and external latches will separate multiplexed address and data lines into pure address lines. Okay, that is one important point. So when we get pure address lines, okay, for that there is an important point, call it as a clock. See here, clock. With the help of clock, I will explain again. So clock. So this clock is a input pin, and this clock pin receiving clock pulse from external clock generator. So in the coming video, I will explain what is a clock generator, how we get clock signal from clock generator. So this clock pin simply receiving clock pulse from external clock generator. So external clock generator gives 5 MHz clock frequency signal to clock. Accordingly, 8086 will operate. So in that clock also we have 4 time intervals. Generally, I will indicate here. For if you take any clock, 4 intervals are there like this. See here. From assume this is the starting point. Assume this is the ending point. See, 1 time period, 2nd time period, 3rd and 4th. Put together we are calling as a 1 clock time. This is clock time. Similarly, T2. Like that, it will go up to T4, T1, T2, T4. Like that, we have 4 time intervals. Okay, now this is called as a clock time period. So now let us see what is clock frequency. 8086 is ready to receive 5 MHz clock frequency. 5 MHz means T equal to 1 by 5 MHz. Nothing but 0.2 microseconds is the total clock time. So that 0.2 microseconds now dividing into 4 intervals, T1, T2, T3, T4. So T1 is the time where the time period is 0.2 microseconds by 4 because of 4 intervals. Okay, this is the first part of the machine cycle, and these 3 called as a remaining part of the machine cycle. This is called as a machine cycle. T1 to T4 call it as a machine cycle. Like that, clock sending one clock signal or clock related signal with a frequency of 5 MHz. Okay, this pin receives the clock from that particular clock generator. So this is called as a one machine cycle, and it is having 4 sub intervals. Okay, now let us see how these AD0 to AD15 lines are separating into pure address and data lines with the help of ALE. Generally, in the case of timing diagram, I will explain it. So ALE, what is address latch enable? This is very important pin. ALE comes under minimum. So this address latch enable pin must be high during first part of the machine cycle. This is first part. In this time it should be high. Remaining part of the machine cycle it should be low. So during this time what happens? Okay, so during this T1 time, so it will take multiplex address and data lines and make it like a pure address lines and data lines. So at the end of T1, so we get pure address lines, nothing but A0 to A15. Similarly, pure data lines, nothing but D0 to D15 after this interval automatically. Okay, Like that, ALE should be high during first part of the machine cycle only, and should be low during the remaining part of the machine cycle. If you go for next cycle also during T1 time, again ALE should be high, and T2 to T4 time low. Like that, it will take multiplex lines and make it like a pure address line with the help of ALE signal. Okay. So the AD0 to AD15 are multiplexed address and data lines, and these lines are separated into pure address lines and data lines by using external latches and ALE signal, and this ALE should be high during first part of the machine cycle, nothing but T1 time only. Okay, and because of this high during T1 part of the machine cycle, it will separate multiplex lines into pure address lines after T1 time. Okay, like that we get address lines. Address lines are separating, remaining lines are data lines only. Okay, right. This is about address lines and data lines, how they are separating. Right. Now coming to other address lines here, A16/S3 to A17/S6. Okay, these four. 38 pin numbers, 35, 36, 37 and 38. So these four are also multiplexed lines, but multiplexed address with status. So your address lines are multiplexed with status lines. So here we separate four multiplexed status lines to pure address lines and pure status lines with the help of another latch and ALE signal. Okay, here also ALE should be high during first part of the machine cycle, and remaining time it should be low. So because of that arrangement, what happens, we get four more address lines are separating in addition to A0 to A15. So with the help of another latch, we get four more address lines. Those are A16 to A19. A16 to A19 lines are also coming, and we have one more here. One more line, A16 okay, A16 to A19, like that 20 address lines are separating by using 3 latches and one ALE, and should be high during T1 time. Now let us see functioning of S3 and S4 is very important with help of, now because S is a status. So based on the status lines, 8086 performs different functions. For example, if you take S3 and S4, okay, depending on the selection of S3 and S4, let us see what happens. See this point, okay, again I will come back to pin diagram. So based on the pins S3 and S4, the 8086 may select suitable segment registers. We know already in 8086 we have 4 segment registers: port segment register, data segment, stack segment and extra segment. So whenever S4 and S3 both are 0 zeros, then your 8086 will take extra segment memory or extra segment register. If it is 0, 1, it will take stack segment. If it is 1, 0, it will take 1, 0, then it will take port segment. Or sometimes no segment also. If it is 1, 1, it will take data segment. Like that, your 8086 may take a suitable segment register based on the selection of status lines S3 and S4. Because of 2 inputs, we have 4 combinations. Depending on the combination, the corresponding segment register will be taken into account. That's why S3 and S4 are also equally important. Similarly, let us see other status lines here. We have 3 more status lines are there. Okay, these 3 status lines comes under maximum mode. Let us see how we get how we are selecting this set. Okay, these set are these A means 24 to 31. Whether we are selecting left side signals or right side signals decided by pin number 33. What is the pin number 33? Mn by mx bar. See, whenever my Mn by mx bar is 1, then we are selecting minimum one. Mn is minimum, mx bar is maximum bar. If it is 1, then we are selecting minimum. So if it is 1, we get this 8 comes into picture. Whenever mx bar is 0, means Mn by mx bar is 0, then we are selecting maximum mode. If it is maximum mode, we get these 8 pins into account. Now, depending on the S0 bar, S1 bar and S2 bar, again processor performs different operations. Whether the processor wants to read data from memory or send data to memory or reads data from input port or sending data to output port. Okay, which operation processor is performing, that is decided by these 3 pins. Let us see what is the functioning of S0 bar, S1 bar and S2 bar here. So here S0 bar, S1 bar and S2 bar gives information about which operation processor is performing. So here if S0 bar, S1 bar, S2 bar all 3 are zeros, which operation processor performs? Processor performs interrupt acknowledgement. It gives information to external peripheral devices, that is ready. Your processor is ready to execute the instructions that are present in the external peripheral. Like that, it will send interrupt acknowledgement signal. If it is 001, then processor performs IO read, means processor reads data from IO device. If it is 010, then processor performs IO write operation, means processor writes data to IO device. If it is 011, processor performing halt. Halt means like a waiting. Okay. Now, if it is S2 bar, S1 bar, S1, here if it is 100 combination, because 3 inputs, 8 combinations. 100 means fetching the opcode. Nothing but in BAU there is an instruction byte queue that will fetch the opcodes, right? So when it is fetching, whenever it is 100, then opcode fetching is possible. If it is 101, memory read operation means processor reads data from memory. If it is 110, memory write operation, processor writes data to memory. If it is 111, means all three are inactive because bar signal, if you give once, then they are inactive. Inactive or passive, so processor may not perform any operation. Like that, the selection of these three status lines will decide whether the processor performing a read operation or write operation or acknowledgement or halt, like that, fetching. Okay, that information is presented based on these three signals, and these two signals will give you selection of segment registers. Okay, coming to other one, there is another one, BHE bar slash S7. It is also a multiplexed pin. BHE bar slash S7 is also multiplexed pin. This pin is also separated into pure BHE bar and S7 with the help of again ALE and latch. Okay, so here also during the first part of the machine cycle, ALE must be high. Okay, then after that what happens? We get BHE bar separately, S7 separately. So based on the selection of BHE bar and lower address line A0, processor performs different functions. See here, based on BHE bar and lower address line A0, processor performs many functions. Let us see what are those. See, based on the BHE bar and A0, processor performs many functions. For example, BHE bar is 0, A0 is also 0. Then processor selecting, okay, accessing a whole word means it will take complete 16-bit data will be accessed by processor. If it is 00, if it is 01, processor access only upper byte from which address? Odd address. From odd address, it will take upper byte from odd address. If it is 10 combination, so processor access lower byte from even address. Lower byte from even address. If it is 11, none, no operation, no data accessing is possible. So in data accessing also, whether the processor access complete 16-bit data or processor access only upper byte from odd address or lower byte from even address, that is decided by BHE bar and A0 signals. These two are also important. Okay, this table is also important. It's not about to S2 bar and how they are important. This is also important. Let's come back to again. So like that we have BHE bar and S7 also. Okay. Now let us see what is ground. Let us see this pin. So ground pin. Generally this pin one is connected to ground. Okay. So generally in some cases with the help of regulated power supply, in that also ground. That ground is connected to pin 1. Okay. This pin provides protection against overcurrents or short circuit problems. Now other pin is VCC. VCC is a power supply pin, and generally 8086 requires 5 volt supply. 5 volt supply. Okay. Now what are the remaining pins here? NMI. NMI is a non-maskable interrupt, and it's a type 2 interrupt. This is a non-maskable interrupt. Is one type of interrupt, and that too it is a type 2 interrupt. Among all interrupts, this NMI is having highest priority. Okay. If any external peripheral device requesting the processor, then okay, that external device will giving the request to request through NMI, then processor will do that particular work immediately because it is having highest priority. Then other one is INTR. INTR is interrupt request signal. Okay, this INTR is in combination with INTA bar. These two are important. INTR is interrupt request signal. INTA bar is interrupt acknowledgement signal. So what is INTR? Interrupt request means, for example, the external peripheral device wants to execute its instructions with the help of processor. In that case, what happens? External device or external peripheral device sending request to interrupt request to processor with the help of INTR. Okay, with the help of INTR, interrupt request pin. So then processor receiving that interrupt request from peripheral. If processor is ready, it will send the signal interrupt acknowledgement bar signal. So whenever if peripheral receiving interrupt acknowledgement bar from a processor, then the processor will execute those instructions. Means the instructions that comes under peripheral will executed by processor after receiving INTA bar signal from the processor. Okay, so these two just for executing the instructions in the peripheral. One for requesting from other peripheral. This is the acknowledgement coming from the processor. Then clock. Anyway, I already explained. Clock is a pin. This pin receives clock signal from external clock generator. Then ground. So we have two grounds are there. Sometimes we go for analog to digital or digital to analog. Okay, for that reason we have two grounds. One for analog ground, other for digital ground. Then VCC is a power supply pin. Okay. So coming to reset, so this is very important one, and this reset must be for any new programming or any new instruction execution. This reset must be activating for at least 4 machine cycles. At least 4 machine cycles. Okay, because of reset, what happens? Except code segment register, all other segment registers are cleared. Similarly, flag register is also cleared. Okay, so if reset is occurred, what happens? Except code segment register, all segment registers are cleared, and flag register is also cleared, and code segment register fetching the address 4FH. So your code segment register fetching which address? 4Fs H, and 8. Okay, after a reset, what happens? Your processor will execute the instruction at an address 4F0H, at an address 4F0H. Okay, 4F0H. Okay, from this address, processor will execute the instructions. Okay, after executing reset. So what is the reset? Reset should be activating for at least 4 machine cycle, and because of reset activation, what happens? All segment registers except code segment register are cleared, and flag register is also cleared. Okay, and the code segment register is holding with the value 4FH, and the processor is executing the next instruction at an address 4F0H. Okay, this will happen if reset is activating. Then ready. Ready signal indicates information to external peripherals that the processor is synchronizing with the external devices. Whenever if ready is inactive, then what happens? Your processor is not synchronized with the external peripheral device. If ready is activating, it indicates that external peripheral devices are synchronized to processor. Okay, like that ready is required. Test bar signal. This is also very important. Test bar testing. So this test bar should be 1. Then it indicates that processor is in wait state. Okay, or it will execute wait instruction. Whenever test bar is 1, then it indicates processor is in wait state. If it is 0, then it will comes out of the wait state and it is ready to execute the instructions. So test bar gives the status of the processor, whether the processor is in wait stage or general stage. If it is 0, it comes out of the wait instruction. If it is 1, processor is in wait instruction only, or wait stage only. Okay. Now coming to read bar. Okay, this is another important pin, read bar. Do you know what is read bar? So read bar pin. So this read bar bar, it's a bar. Remember, read bar. When this pin is activating by giving 1 or 0, 0. Bar means 0. So whenever read bar is activating, then 8086 reads data from external memory or external IO device. Okay, if this read bar is activating, then only it will read data from external memory or IO. Okay. Then other two, these two are first we'll see write bar signal. So now the first we'll discuss minimum mode signal, later maximum. So now coming to write bar. Whenever write bar is activating, then what happens? Processor sending data to external memory or IO device. Nothing but processor writes data to external device or IO device. Sending. Write bar means sending. Read bar means receiving. Then M by IO bar signal. This is also important. M by IO bar signal. If M by IO bar equal to 1, then we are selecting memory. M is memory, IO is IO device. If it is 1, then 8086 performing data access with memory. If it is 0, 8086 performing data accessing with IO. For example, M by IO bar is 1. Then what happens? Processor reads data from memory or sending data to memory. If it is 0, processor reads data from IO or sending data to IO. Means M by IO bar signal is in combination with read bar and write bar. Okay. For this, let us see one small table we can understand. So here, see this table: read bar, write bar, M by IO bar. For example, read bar is 0, so it is active. Write bar is 1 means inactive. M by IO bar is 0 means which one here I am selecting? IO bar means IO. Here because bar signal means here I am giving 0, so we are selecting IO. We are selecting read. So which operation processor performing? IO read. Similarly, for example, write bar is 0. Okay, so read bar is 1, so it is inactive. M by IO bar is 0. Which operation processor performing? IO write, because the write is selecting, IO is selecting, so IO write bar. IO write operation. For example, read bar is 0, write bar is 1. M by IO bar is 1. Then what happens here? We are selecting memory, here we are selecting read. Then which operation it will perform? Memory read. Unfortunately, read bar and write bar both are zeros. Then okay, processor may not perform any operation because it won't perform read and write at a time. Similarly, read bar and write bar both are 1s, then both are inactive. In that case also no operation performed by the processor. Like that, this table is also very important. So, okay, how we perform read or write depending on the selection of M by IO bar, read bar and write bar pins. Now come back. Like that, we have read bar and write bar and M by IO bar. Now other important point is DT by R bar. What is name DT by R bar? DT is data transmit, R bar is receiver bar. Data transmit / receiver bar. So here, if it is 1, then your 8086 performing data transfer operation, means it will send data to other devices. Okay, if it is 0, receiving. So 8086 receiving data. Okay, DT bar indicates whether the processor is performing sending or receiving, whether the processor is sending or receiving. If it is 0, processor receiving the data from external device. If it is 1, data is transmitted to external device. DT is data transmitter slash R bar is receiving. Bar is there here. Okay, then other is DEN bar, data enable bar. This is also very important. So if the signal is activating, then only data is enabled. Otherwise, the data is disabled. So we are not performing any data accessing. So for minimum mode operation, always DEN bar should be enabled. Okay, it is enabled by giving 0. Then ALE, anyway I already explained, and this should be separate multiplexed address and data lines, similarly address and status lines into pure address lines and data lines or status lines. Okay, during first part of the machine cycle, and it should be high. Right. So what about other INTA bar also I explained. Now coming to hold and HLDA, these two are also important. Okay, these two functions are similar to functioning of these two in maximum mode. So consider carefully, hold and HLDA. Hold signal, HLDA means hold acknowledgement. What is the full name of HLDA? Hold acknowledgement. First hold, then HLDA. Right. So put together these two pins, 30 and 31. See here, these two pins are used by external master for requesting processor system bus. See here, these two pins are used by which one? External master. Okay. For which purpose? For requesting the process system bus. What is system bus? It's the combination of address bus, data bus and control bus. So because of these three buses are present by 8086, it is a whole, it acts like a one processor and it will execute all instructions because of system bus. So now your external device or external master also asking process system bus with the help of these two signals. For example, external master wants process system bus, then it will send the signal, hold signal to processor. If processor is ready, it will send hold acknowledgement. Okay, hold acknowledgement. Then after receiving the hold acknowledgement signal from the processor to the external peripheral, then external peripheral is takes the process system bus and execute its own instructions. Okay, in those cases these two pins are important. So coming to maximum mode, in that also first we will see request bar by grant 0 bar, request bar by grant 1 bar. So the functioning of request bar by grant 0 bar and request bar by grant 1 bar are similar to the functioning of hold and HLDA in minimum mode. So here also these two pins are used to access the process system bus by external master. So but here at a time two masters can requesting the processor for accessing system bus because of two pins, request pin grant 0, request pin grant 1. Like that two external masters can request the process system bus. But in these two, request by grant 0 bar is having highest priority than request by grant 1 bar. Means if any master requesting the processor with this pin, it is having high priority than this. Then first master will give you a grant to this, processor will give you grant to this master first, then later this master. Okay. Like that we have two request and grant signal. So request is input, grant is output from the processor. Okay, similarly here also same. So these two pins are similar for these two, only for accessing the processor system bus. Okay, right. Then what is a lock bar? Lock bar is it indicates whether the process system bus is enabled or disabled. If lock bar is activating, what happens? Process system bus is locked by processor, locked by 8086. If it is active, it indicates that no master is receiving the process system bus. Okay. Then okay, already these three I already explained. Now coming to other two, QS0 and QS1. This is also important. QS0 and QS1 indicates queue status of your queue. We know already in bus interfacing unit there is a 6-byte instruction queue. So status of that particular 6-byte instruction queue is specified by QS0 and QS1. So depending on the QS0 and QS1, let us say queue is empty or queue is ideal, fetching. We have one table. I will explain that. Table QS0 and QS1. Assume both are 0, 0, then no operation in the queue. So queue 6-byte instruction queue may not perform any operation if it is both zeros. If it is 0, 1 combination. So now your queue will take first byte. First byte will be fetched. If it is 1, 0, then it indicates that queue is empty. Queue is empty. If it is 1, 0, queue is empty. If it is 1, 1, then it will fetching the subsequent byte, means next byte. Like that, if it is 0, 0, there is no operation in the queue. If it is 0, 1, first byte will be fetching. If it is 1, 0, it indicates the queue is empty. 1, 1 means subsequent byte, means next byte is fetched from the memory and loaded into queue. Okay. Like that, we can analyze the it is loading. Right. Okay. Like that we can analyze the pin description of 8086. Okay. Now I think you understood what is the pin diagram of 8086 and what is the functioning of each pin, right? Right. So let us see. So thank you for watching this video. Right. Right. So thank you for watching this video. I hope you understood what is the pin diagram of 8086 and what is the functioning of each pin. Okay. So please kindly share my video and subscribe my channel. Right. So thank you so much.